work on the DC to DC converters and working principle of the different types of the converters, modeling, parameter calculation, performance analysis of the DC to DC converter without the controller and control design issues. So mainly we know that one. Okay, before discussing about the directive power converters, okay, first of all, we are going to discuss about the what is the necessity of the power converters. Okay, so basically we know the power system sector. Okay, in the olden days we are using the some integrated system. Okay, we are using the generator and everything basics we know that about this one. We are having the generation, transmission, distribution, and that load. But the nowadays we are moving towards the renewable energy sources. We are moving towards the renewable energy sources, and also most of the thing. Okay, we are using the DC loads. Okay, as a present trend, all moving towards the electrical vehicles. Okay, the main load for the DC supply is the charging of the electrical vehicle. So to charge that electrical vehicle, okay, we are requiring the some DC power supply, and from the renewable energy sources, we are getting the some DC supply also. But here we are getting the one range of the DC supply, but to charge fast charge of the battery, okay, we need to increase the current level. So with the help of the DC to DC converter. So this is the one of the aspect of the what is the necessity of the DC to DC converter. The other one is the okay, here we are showing the different number of the renewable energy sources. Those are the fuel cell, solar grid, and winter grid. Okay, so with the help of these renewable energy sources, okay, to charge this battery, okay, in between, okay, we need to develop the some integrated system. So that's why the similar diagram, okay, the simulation point of view are shown here. Okay, this is the solar PV system and wind power and the fuel cell subsystem. And here we are trying to charge that battery with the help of the some DC to DC converter. So schematic diagram for this on type of the system is the here we are using the some polar PV array, and with the help of the DC DC converter we are trying to battery charge that battery. So and to get the to extract the maximum power from the PV array, okay, here we are using the some MPPT controller. And after from that battery, okay, to charge that load, okay, we are using the some DC load here, or otherwise we are having the DC power available with us. Again we are trying to convert the DC to AC, and while converting the DC to AC we are having the some filter harmonic component, okay, to filter out that one. Here we are using the some filters, and then the pure AC supply we are giving it as a AC load. Okay, so to get the desired AC output, okay, here we are forming the some closed loop system like this. Okay, so here also that means if you want to utilize the solar power system, that is the renewable energy systems. Okay, so most of the cases, okay, we are using the some power converters. Okay, we are observing the different cases of the DC source. Okay, the other application, okay, here is the PV array we are using with the
Hello,
help of the,
sir.
hello.
Excuse me, sir.
Sure.
Sir, did you maximize the screen, sir?
Maximize, no?
It's only showing first screen only.
First slide only.
Only first screen only. Sir, just maximize. Next one. Okay.
Now visible.
Visible, but it's sir. Maximize the screen, sir.
Now, not changing or not? Slides are changing or not?
Slides are changing, but maximize the screen. Like uh, make it a slideshow.
Ah, so here I am using that. Okay, okay. I understood that. One minute. I will close the open board.
Okay.
I think now it's fine.
కింద 77% కింద ఒక సింబల్ ఉంది కదా, దాని మీద క్లిక్ చేయండి. పక్కన ఓకే. నో సార్, పక్కన దాని మీద క్లిక్ చేయండి.
ఆల్రెడీ షేర్ చేసాం అలానే
స్లైడ్ షేర్ కనబడట్లేదు సార్, ఓన్లీ సింగిల్ ఒకటే కనబడుతుంది, ఫస్ట్ పేజ్ కనబడుతుంది. స్లైడ్ షేర్ మీద క్లిక్ చేయండి సార్, అది మ్యాక్సిమైజ్ అవ్వలేదు. ఓకే, మీ ల్యాప్టాప్లో అవుతుందా మరి? నెక్స్ట్ స్లైడ్ క్లిక్ చేయండి సార్, అది నెక్స్ట్ స్లైడ్లోకి మారుతుందో లేదో చూద్దాం. నెక్స్ట్ స్లైడ్ మారిందా సార్?
మా దగ్గర మారుతుంది,
ఇక్కడ మారట్లేదు సార్, ఓన్లీ ఒకటే కనబడుతుంది. ఇప్పుడు ఫస్ట్ స్క్రీన్లో ఉంది, ఫస్ట్ స్లైడ్లో ఉంది. ఇప్పుడు నెక్స్ట్ స్లైడ్కి వెళ్ళింది.
ఇప్పుడు థర్డ్ స్లైడ్.
నో సార్, సెకండ్ స్లైడ్లోనే ఉంది. ఇప్పుడు థర్డ్ స్లైడ్లోకి వచ్చింది. Okay, you can restart the session.
Okay, so sorry for the disturbance. Okay, here we are observing the some of the what is the requirement of the DC to DC converter. Okay, that is the if you are moving towards the renewable energy systems, so here we are requiring the some DC to DC converter, and here also we are using the some renewable energy systems. Okay, fuel cell subsystem, solar PV system, and the windmill. Okay, here to charge that battery, okay, here we are requiring the some DC power. That's why, so with the help of the DC to DC converter, okay, we need to change the one level to the other level. Okay, these are the some other applications. Okay, for the DC to DC converter. And here I am showing the some simple example, that is the PV array DC to DC converter with the help of the some MPPT tracking. With the help of the MPPT tracking, I are trying to get the maximum power from the solar PV system. And then the help of the by connecting the battery, electrical vehicle battery, we are using the DC power, and excess power DC power available with us. Okay, we can convert the same DC to AC. While converting the DC to AC, okay, we are getting the some harmonic components. Okay, to filter out that one, here we are using the some filters, and then the AC supply we are connecting it as to the AC load. Okay, so and to get the desired output, okay, here we are forming the some closed loop system. Okay, later we will discuss about the how to design a controller for that. So this is the some other example of the architecture of the PV grid for the electrical charging system. So here we are using the different sources. One type, okay, we are using the grid supply. Other one, okay, we are using the some renewable energy sources. So by using the bidirectional inverter, okay, here we are trying to convert the some AC to DC, and then by using the some PV array, we are getting the some DC power supply, and finally, okay, here we are getting the some DC power supply. That's why we are using the some DC bus. And with the help of the unidirectional charger, we are trying to charge that one. And if you are having the excess power with us, okay, with the help of the bidirectional DC charger, we are trying to store the some DC power in the battery. Okay, so like that. Okay, here also we are required. There is a requirement of the some DC to DC converter. So this is the hydrogen fuel cell vehicle. Okay, here also we are inside this one. Okay, we are using the some DC to DC converter. Okay, this is the fuel cell stack. With the help of this one, okay, we are getting the some DC power supply, and to drive that one, okay, to charge that battery inside this car. Okay, again we are using the some DC to DC converter. So, and this is the other simulation view of the grid connected charging of fast charging of the battery. And here we are using the some electrical power supply from grid, and with the help of the thyristor voltage rectifier. Okay, here we are converting the some AC to DC here, and the DC we are with the help of the DC to DC converter. We are giving the electrical power supply to that of the battery in the required range of the voltages and current to charge that one. So this is the overview of the DC. That means from this one, okay, we are understanding about the there is a requirement of the DC to DC converter, that is the power converters, okay, for the charging first for charging of the electrical vehicles. So if you want to, that means there are a lot of research gaps in case of the in this integrated system. Okay, we may do the some research work on the how to extract the maximum power from this one, and if you by utilizing the renewable energy sources, how we are able to deliver the electrical DC power supply to charge the fast battery. So that means one area is on the sources. Okay, how we are extracting the more power from the renewable energy sources. The other aspect is the other research option is the you can do the research on the DC to DC converters. Okay, there are different types of the DC to DC converters are there. So that's why from that one also we are able to do the some research on the DC to DC converter area. The other scope of the research is the yeah, increasing the rating of the charging storage capacity of that battery with the help of the different materials in the electrical vehicle battery. So that means there are different areas. Okay, one is in the source side, other one is in the conversion side, other one is in the load side. Okay, so in this today's presentation we are moving mainly discussing on the power converters, okay, which are used for the fast charging of the electrical vehicles. Okay, so here mainly we are discussing on the what is the necessity of the DC DC converter here. Okay, what is the necessity of the DC to DC converter in this type of that application? That means here we are trying to integrate the renewable energy system with the electrical vehicle. So in between, okay, we are using the some DC to DC converter. So in that using the DC to DC converter, what is the main necessity of the DC to DC converter here? Nothing but the so as we seen in the previous cases, okay, either if you are using the source is the renewable energy source, or if you are using the some grid connected system, whatever may be the source, okay, the first one is the we need to get the regulated DC output from the DC to DC converter. The main requirement is the regulated DC to DC output, regulated DC to output. Okay, so the sources may be the battery or maybe the from the AC supply uncontrolled rectifier. We are converting the AC to DC. Whatever may be the source. Okay, here we need to get the regulated DC to DC output. Okay, here the question is why we are getting the variable load in the variable voltage at the source side. Okay, why what is the variable why we are getting the variable DC for that load. Okay, so that is the main reasons is the first one is that there is a chance to get the variations in the battery performance, battery variation. That means there due to the aging effect or some other factors on the affected on the performance of that battery. So that's why the first one is the there is a battery variations, or if you are using the grid connected system, there is a chance to get the AC supply voltage changes. And if you are using that load, okay, the load also some cases the load may be varying. And also once you are designing the DC to DC converter parameters, okay, due to the some external factors, okay, there is a chance to get the change in the values of the parameter. Okay, so here whatever may be the condition, okay, one is the you may get the by changing the variation of the battery voltage variation, or AC voltage changing, or load changing, or the parameter whatever may be the case. Okay, we need to get the regulated DC. So for that purpose, okay, we are requiring the DC to DC converter. How we are converting the using the DC to DC converter is the one is with the help of the solid state devices. Okay, with the help of the solid state devices, okay, we are able to convert the DC value from one value to other value. And in some special applications, okay, we are requiring the some isolation also. As the current range is increasing beyond certain value, okay, we need to go for the isolated DC to DC converter. So that's why, okay, here we are requiring the some isolation. For this purpose, okay, we are using the some transformer, pulse transformer, in case of the polytronic converters. Okay, so that means, okay, based upon this requirement, okay, these converters are classified into the two categories. One is the non-isolated DC to DC converter. Other one is the isolated DC to DC converters. The examples of the non-isolated DC to DC converters is the buck converter, boost converter, buck boost converters, all these things. And the simple examples for the isolated DC to DC converters are the flyback, push pull, forward, and full pitch converter. Okay. So these are the different types of the categories. Okay. In today's session, okay, we are going to discuss about the both the type of the non-isolated and the then the isolated. Okay, we are going to discuss about the four different types of the converters. Okay, and we are trying to finally we are trying to develop the complete system like this. Okay, so that we everything, okay, by designing the controller everything, okay, we are trying to design the complete system like this. Okay, so with this analysis, okay, if you want to do the research on the field of the DC to DC converter, so this is the roadmap to do the some research in the field of the DC to DC converter. Here for the simple example I am taking the some high switching frequency converter. So, if you want to do the research in the field of the DC to DC converter, at the first stage, we need to concentrate on the working principle of that particular type of the DC to DC converter. And internally, if there is some isolated DC to DC converter are having the different types of the connections, so that's why. So, we need to observe the what are the different types of the connections are there, and then based upon for all the one, okay, we need to observe the working principle. And then, okay, if you want to develop the same converter in the some of the software, some MATLAB, Scilab like that, in that case, so we need to derive the mathematical model for the chosen converter. Okay, so that is the second. In the second step, we need to go for the modeling techniques. Okay, why the modeling technique is required, and later I will explain again. So in the modeling techniques, okay, there are different types of the modeling techniques are available. One is the some small signal modeling, state space modeling, and in case of the digital also small signal dexterity model is there. In today's presentation, mainly we are concentrating on the state space model for the different types of the converter. And then after completion of the modeling technique, okay, we need to select the input parameter and output parameter. Based upon that one, we need to design the some of the parameters for the power stage. So after designing the power stage components, okay, we need to observe the behavior of the converter without any controller. Okay, after observing the behavior, so if you are observing if there is a requirement for that controller, then we need to design a controller. So to design a controller, there are different types of the controllers are available. Some of the one is analog converter, digital converter, some other types of the converter. So in the today's session, okay, we are going to discuss about the how to design a classical controller, simple classical voltage mode controller, and then we are going to discuss about the some other soft computing technique. One is that is the fuzzy logic controller for the different types of the systems. Okay, so this is the roadmap to design that one. Okay, and finally, okay, we need to identify the where we are using the design system. Okay, so this type of the converter they are using here. Okay, but we may in our applications, okay, we are choosing the electrical fast charging. Okay, like that, if you want to do the research, okay, as a research scholar or the some project finalist students, or if you wherever whenever whoever the doing the research in the field of the power converters, okay, you need to make the roadmap like this. Okay, based upon that one, so we may observe the step by step procedure, okay, to do that research. Okay, so in the first step, okay, we are discussing about the working principle of the system. So for that purpose, okay, first case, okay, at very start, okay, we are choosing the some simple buck converter. So then we are moving for the buck converter, boost converter, and some other KY converter like this. Okay, these three are the non-isolated DC to DC converter. In the isolated DC to DC converter, again we are choosing some one of the simple active clamp forward converter. Okay, So this is the working principle of the buck converter. Okay, most of the people we know that one basic operation of this one. So again, for the why I am choosing the simple buck converter, nothing but the step by step I want to move towards the uh, non-isolated. Okay, so these are the some of the converters. Okay, if you want to understand the principle of operation of this one, first of all we need to know the basics behind that one. That's why, okay, just I will review the basic operation of that buck converter. Okay, this is the basic circuit of the buck converter. Here we are applying the DC supply, and at the here I am connecting the some resistive load. Okay, for this across this one you need to get the some DC power supply. So to convert the DC value one level to other value, here I am using the two solid state devices. One is the MOSFET, other one is the diode, and these two are the filter components L and C. So if you are giving the turn on pulse to that Q1, okay, so it is simply acts as a short circuited. As it is standard, it simply acts as short circuited, and the current direction during the on period is like this. And if you are getting the positive supply to the cathode, okay, the diode D1 is gets reverse bias, and the current is passing from the source to the inductor and through the capacitor and the load, and then combining these two are coming to that of the minus. Okay, so during this case, okay, the voltage across the load is equal to that of the input voltage. That's why this is the voltage during the on state. Okay, so and second case, what happens if you are giving the turn off pulse to that of the solid state switch Q1, so it simply acts as a open circuited, and there is no direct connection between the source and that load. So these two are already charged, and the property of the inductor is that it does not allow the sudden changes in the current. That's why both the capacitor and inductor will try to deliver the power supply to that of the load through the diode D. Okay, as it is there is no supply nothing but the from this capacitor try to discharge. That's why anode of the diode gets forward biased, and then so your current is like this. So then during the aha period, okay, we are getting the voltage is the V. So by to derive the how the voltage, okay, relation between the input voltage and output voltage, just we are taking the volt second balance of this one. Okay, during the positive cycle the inductor current gets charged, that's why the current is linear increasing, and during the off period of the Q1, so the charge, the current is decreasing. That's why the inductor current is discharging like this. Okay. So to derive the relation between the input voltage and output voltage, okay, here I am taking the volt balance equation. So for the off cycle Vn minus V, the on period is the D times of the Ts. There, that's why Vn minus V into D times of the Ts equal to off period voltage is the V, that is the 1 minus D times of the Ts. Okay, that's why V into 1 minus D times of the Ts. Okay, finally, so we are deriving the relation is the V naught equal to D times of the Vn. Okay, where D is the duty cycle. This duty cycle is always in between the 0 to 1. That means it not must not be 1 or must not be 0. It is between the 0 to 1. That's why the output voltage is always less than that of the input voltage. That's why it is called as a buck converter. Okay, so this is the basic working principle of the buck converter. Okay, similarly we can observe the other one. Okay, that is the boost converter. Here also similarly, if the solid state switch Q1 is turned on, okay, during the on state the equivalent circuit is like this. The inductor gets charged, and the diode gets reverse biased. Because of it is here it is forming the short circuit path, that's why diode gets reverse biased. During this case the capacitor will be deliver the supply to that of the load, and whenever the switch is off condition, it simply acts as open circuited. During that period your input voltage goes to that of the load. Okay, so corresponding to on period and off period, these are the relations. And by similarly, if you write the volt balance equation, okay, we are getting the V output voltage V into ornament D equal to V in times. Okay, therefore the in relation between the input and output voltage is the V naught equal to 1 by 1 minus D times of the Vn. Therefore, the D values we know always in between the 0 to 1. That means the V naught value is always greater than that of the Vn, because of this value is always in between the 0 to 1. That's why the output voltage always more than that of the input voltage. That's why it is called as a boost converter. Okay. So similarly, taking the some other type of the converter. Okay, this is also similar to that of the KY converter. Most of the research is going on the KY converter for in the case of the non-isolated DC to DC converter. Okay, so this buck and boost is old one. So most of the research is going on the KY converter. Okay, and loop converter like that in the field of the non-isolated DC to DC converter. Okay, so this is the KY converter. Okay, this is the basic circuit of the KY converter, and in the KY converter also there are different configurations are there. So here in this presentation we are taking the only one configuration. So here similarly here they are using the two switches Q1 and Q2, and they are assuming that if the Q1 is turned on, Q2 must be turned off, and if the Q1 is turned off, Q2 must be turned on condition. Like that, they are considering the two different cases. So if the Q1 is turned on, the equivalent circuit is like this. The current path is plus 2 short circuited path as compared to the diode resistance. Okay, it is are having the very low resistance value. Always we know the current is passing to the low resistance path. That's why the current path during the on period is the source to the Q1 to the filter capacitor CB and the load components L0 C0. Okay, so it is simply acts as open circuited. The other case, if the Q1 is open circuited, Q2 is turned on. That's why source to diode and then CB, and then okay, that means during the positive half cycle CB gets charging, and during the negative half cycle CB gets discharging as the current direction is changing. Okay, so like that we are getting the basic principle of operation for the KY converter. And again, if you write the volt balance equation and if you derive the relation between the input voltage and output voltage, okay, the output voltage is 1 plus D times of the Vn, and we know the D is in between the 0 to 1. That's mean output voltage is always greater than that of the input voltage. That means it is similar to that of the boost converter. Okay, so these three are the non-isolated DC to DC converters. One is the buck, boost, and the KY converter. And then if you are getting the, if you want to get the more current in the output, okay, that means first for the fast charging of that EVs, okay, so we are requiring the huge amount of that current. But here we need to, if you want to get the more load current and less input load output voltage, and that means low voltage high current applications, okay, we need to move towards the isolated DC to DC converter. Okay, so in this case we are going for the we are trying to derive the sum of the converters based upon the buck configuration. Okay, this is the dotted lines representing the simple buck converter, and here we are taking the simple forward converter. That means for the purpose of isolation, here we are using the some pulse transformer, and we are giving the DC input, and this transformer we are using for the purpose of the isolation. Okay, but here the problem with the transformer is the, as we know that one, in case of the AC it is working because of we are getting the alternating current at the input. That's why there is no problem with the magnetic saturation. But if you are using the DC here, after certain time interval, okay, it is getting charge, there is a saturation problem. Okay, that's why that means at each and every cycle, every switching cycle, we need to set and reset this transformer, okay, to work the transformer function. Okay, in each and every cycle we need to set and reset the this transformer. For that purpose, okay, we are having the different types of the resetting techniques. I'm not going inside of this one. Okay, just I'm going to that of the as compared, there is a lot of techniques are available to reset the transformer of the buck derived forward converter. Okay, but one of the configuration which is called as a active clamp forward converter, having the more advantages than that of the remaining type of the configuration. That's why, so in today's presentation I am taking the this active clamp forward converter. Active clamp nothing but the to reset this transformer. Here we are connecting the some extra capacitor and the MOSFET, another MOSFET. Okay, so during the positive half cycle the current path is like this, and during the negative half cycle we are taking the capacitance Ec such that to get the more voltage than that of the input voltage. That's why, so during the off period of the main MOSFET Q1, okay, the your Cc getting your CC is getting more than voltage across the CC is getting more than that of the CC is getting more than that of the okay, CC is getting the more than voltage across the clamp capacitor getting the more than that of the slide change out. Okay, CC is getting the more than that of the voltage across the clamp capacitor getting more than that of the source voltage. That's why you are getting the resetting. Okay, that means as compared to the remaining techniques, okay, these are having the more advantages. That's why so we are moving towards the active clamp forward converter. The benefits of the active clamp forward converter technique is that there is no requirement of the additional reset winding like sumper, and it is allowing the higher duty cycle and wide range of the input. So and zero voltage switching possible in case of this one. Okay, like that there are different advantages are there for the active clamp forward technique. Okay, and then in the active clamp also there are different configurations are there. One is the active clamp forward converter with the half wave rectifier, active clamp forward with the center tapped, and that means to get the various ranges of the output voltages in the load. Okay, here we are using the different configurations. One is the this is the active clamp resetting technique for the forward converter. In the output side, okay, that means in the secondary side of the converter, we are trying to uh, increase the voltage values. That's why they are using the different configurations: software rectifier and full wave rectifier, and the current doubler circuit and the interleaved converter. Like that, in the active clamping also there are different configurations are available. So and before that means here in this presentation we are using the some simple active clamp forward converter. Just we will observe the so what is how the active clamp forward converter will work. Okay, so the first case is the power transfer mode. So this is the equivalent circuit for the power transfer mode. Okay, here we are using the DC supply and the current path is like this to the primary winding, and Q1 is turned on and current is like this. Okay, where IP is the primary current, IM is the magnetizing current in the transformer. Okay, LM is the magnetizing inductance of the transformer. And in this case secondary, the diode D1 gets forward biased and diode D2 gets reverse biased. That's why the primary side input voltage will be transformed to secondary by the gain of the Vg by N. So that's why it is called as a power transfer mode. Okay, so and then similarly we know the basic buck operation. L and 0 L0 C0 are the charging during this period, and the load power same source will be delivered the power supply to that load. Okay, this highlighted is the period of the power transfer mode. Okay, the second mode is the resonant interval. So in the resonant interval nothing but the here Q1 is turned off and body diode of the Q2 is conducting. Okay, the body diode of the Q2 is conducting. That means here the resonant condition is the delay time between the main transistor main MOSFET Q main turned off and the Q are turned on. Okay, now Q2 Q1 the delay between the turn on period of the Q1 after turning off of the Q2 turning on of the Q2 and after turning off of the Q1 is called as the resonant period. Okay, during this period this body diode conducting and CR and the inductance LR is in the resonant condition. So that's why it is called as a resonant period. Okay, so the third condition is the third mode is the uh, magnetizing current zero. In this case magnetizing current zero. In this case the second MOSFET Q2 is turned on and Q1 is completely turned off. And as I said already said, the voltage across the capacitor VC becomes more than that of the applied voltage because of we are choosing the clamp capacitor values like that. So during the first power transfer mode, the CC gets charged. That's why here you are getting the more voltage than that of the source voltage. So that means in this case, in this period, okay, the clamp capacitor will be acts as a source for this primary circuit. That's why the current gets a reverse bias through the primary winding. The current is reversing to that of the supply. That's why this active clamp circuit are having the more benefits than that of the remaining resetting configuration. Okay. So here the current direction reverse nothing but the diode D1 gets a reverse bias, D2 gets forward bias, and similarly buck operation. Okay. So the third one is the again before turn on of the Q1, after turning off of the Q2, again we are getting the fourth resonant condition. So this is the fourth resonant condition for the active clamp forward converter. Okay, so this is the basic operation of the DC to DC converters. Okay, in our presentation, okay, we are observing the first one is the working principle of the simple buck converter, boost converter, KY converter, and the active clamp converter. So next stage, okay, we are moving towards the modeling techniques for the different types of the power converters. Okay, so now the second one is the modeling. Okay, here there are different types of the mathematical modeling techniques are there. Mathematical modeling nothing but the representation of the physical phenomena by its mathematical equivalent. Okay, modeling nothing but the representation of the physical phenomena by its mathematical equivalent. Okay, so in that there are different techniques are available. One is the state space averaging technique, other one is the switching averaging technique, third one is the circuit averaging technique. So in the first case, we are using the state space averaging technique. So this is the basic introduction to that of the state space. So directly I'm moving for the state space model of the state space model for the buck converter. Just here I'm requiring the some of the formulas. That's why just I'm using the some board also. Okay, here this is the state space. So how to derive the state space average model? Nothing but the since the at a very anybody interested to do work on the power converters area, just to note down the state space model. Nothing but the it is containing the x dot equal to ax plus the state space model. Nothing but the it is the x dot equal to ax plus bu. So that means the state equation is the x dot equal to ax plus bu. So in this x is the state variable, x is the state variable. So if you want to form a state model, whatever the variable you are chosen as a state, while writing the equation for that circuit, you need to get the derivative of that one. Okay. So the state model containing the one equation is the state equation that is called as x dot equal to ax plus bu. The one important thing, okay, while deriving the state space model, we need to remember about whatever the variable you are chosen as the state variable x. While writing the equation, you need to get the derivative for that. Okay, derivative for that. Okay, so that's why. Okay, in this case, I am taking the inductor current IL and the capacitor voltage, inductor current IL and the capacitor voltage as a state variable. Look, that means in here I am considering the current through the inductor current IL and the voltage across the capacitor is the V as a state variable. That means I am considering the two state variables. One is the inductor current IL, other one is the voltage across the capacitor, that is the V as a state variable. And I am trying to write the state equations, okay, by writing the loop equation or node equation. Okay, first of all, here I am trying to write the uh, voltage across the inductor value. Voltage across the inductor VL equal to Vn minus output voltage. The voltage across the VL inductor voltage VL equal to input voltage minus voltage across the circuit. Okay, voltage across the circuit is the V. That's why VL equal to Vn minus V. So where VL nothing but the voltage across the inductor. The expression for the voltage across the inductor is the L into dIL by dt, that is equal to V in minus V. L into dIL by dt equal to V in minus E. Okay, where, as I already told that one, whatever the variable you are chosen as a state variable, in the state equation, you need to get the derivative of that one. That's why, so for this relation, I am getting the dIL by dt equal to Vn by L minus V by L. Okay, this is the first state equation I am getting. And the second state equation is the, I am writing the expression for the current through the capacitor IC. Okay, the current through the capacitor IC. Okay, the current through the capacitor IC equal to current through the capacitor IC equal to inductor current IL minus load current to I. The expression for the load current I is the V by R. Therefore, that is equal to IL minus V by R. The expression for the IC is the C times of D into Vc by dt. So where I am choosing the V as the state variable, in the second equation I am getting the derivative for that. Okay, that's why, therefore dVc by dt equal to IL by C minus V by RC. So this is the first equation, dIL by dt equal to Vn by L minus V by L. This is the second equation, dVc by dt equal to IL by C minus V by RC. Okay, so that's why, okay, dIL by dt I am written here as I dot, dVc by dt I am written as the V dot, and this IL I am taken here, and the 1 by output voltage I am taking the second state variable, and this is the V in input voltage. So here there is no inductor relation in this case, that's why the inductor term is 0, and there is a V term, okay, that is the 1 by L, that's why I am written the 1 by L here, and there is input voltage term, that is 1 by L, that's why I am taking the 1 by L. And the second case, Vc dot V dVc by dt is the V dot I am written here, and in this case there is IL term, that's why that is the 1 by C, that is 1 by C, and the V dot output voltage 1 by R minus 1 by RC minus 1 by RC. There is no input term here, that's why I am taking it as 0. Okay, and this is like that, we need to write the expression for the input voltage. Okay, that means expression for the state variables. Okay, by writing the loop equations or the node equations, based upon that one, we need to form the state model for this. So like that, by writing the equation for the state variables, okay, we are writing this one. Okay, here we need to get the doubt about the what is the iz here. Okay, what is the iz here? So in this case, I already at the time of the necessity of the DC to DC converter, I told that one there is a chance to get the variation in the supply, and there is a chance to get the variation in that load, and there is a chance to get the variation in the parameter value. Okay, so to observe the variation in input voltage, we may vary the input voltage. To observe variation in the L and C, we may put the different values of L and C. And to observe the variation in the load, artificially I am creating the some extra disturbance here by using the another current source IZ. So regarding that one, I am getting this IZ term here. Okay, so for the forward input voltage case, in the first loop equation, there is no direct relation between the IZ and Vn loop. That's why there is IIZ term is there. But in the output case, I am getting the IZ by C. That's why in the for the second equation, I am getting the 1 by C term here. Okay. So this is belongs to that of the on state of the buck converter. This is for the on state of the buck converter. Similarly, we will move forward for the just a minute. Okay, similarly, we will move forward for the second case, that is the off state of the main MOSFET. So in the off state also, for the off state also, we need to for the off state also we need to write the same input voltage equation, that is the voltage across the inductor equation and the current through the capacitor equation. The same thing we need to represent the matrix form like this, and finally we need to average the both the states based on the on period and the off period. Okay, this is the D is the on period, D is the D is the on period, and this 1 minus D is the off period, and A on is the matrix corresponding the matrix. A on is the matrix corresponding the on period of the switch, and B on is the B on matrix corresponding the on period, and A of is the matrix corresponding the off period, and B of is the matrix corresponding the off period. So from that one, by taking the average over a switching period d times of A1 and 1 means d times of the A of, we are getting the final A matrix and B matrix here. A matrix and B matrix corresponds for the state model for the buck converter. Okay. And again, in the as we saw that one, there is a chance to get the variation in the parameters. That's why we are using the some small signal. We are considering the some small signal variations. Okay, for that case, we are taking the x equal to capital X plus x cap, where x is the DC quantity and x cap is the variable quantity, and u is the DC quantity and u cap is the uh, U cap is the small signal variation in the input voltage, and D is the small signal variation in the uh, D cap is the small signal variation in the duty cycle. Okay, like that, by considering this one, finally we are trying to get the state model for the buck converter. Okay. So second case, okay, we are moving for the same similar manner. We can derive the expression for the boost converter also, corresponding to the on state by writing the inductor current, inductor voltage equation, and the capacitive current. Okay, so simple thing I can remember that. Okay, if you want to do the derive the some small state space model for the power converter, so here one thing I want to say that one, you need to choose the inductor current and capacitor voltage as a state variable, and the you need to write the expression for the inductor voltage and capacitor current. Okay, we need to that means in the power converter to form the state model, one important note is the, so while choosing the state variable we need to select the inductor current and the capacitor voltage as a state variable, and to form the state model we need to write the equations for the inductor voltage and the capacitor current, that means vice versa. Okay, we are choosing the inductor current, capacitor voltage as a state variable, and we are writing the expression for the inductor voltage and capacitor current. Okay, so that is the one important thing. The other important thing is the order of the state space model is equal to that of the number of energy storage element in the circuit. Order of the state space model equal to the number of storage elements in the circuit. Okay, in the previous case we are having the two storage element, that's why we are getting the 2 by 2 matrix, and here also boost converter also we are having the two storage elements, and this one is the 2 by 2 matrix we are getting. Okay, so this is for the on state of the main MOSFET, and this one is the off state of the boost converter, off state of the boost converter. Again here also I am considering the inductor current and the output voltage as a state vector, and input u and the is a Vn. So based upon that one, again we are trying to form the state model by taking the average d an times of the d times of an and 1 is d times of the r. So here also I am taking the small signal perturbation, and finally we are getting the state model for that. Okay, once you are having the state model, you can build the circuit. Once you are having the state model, okay, you can build the circuit for the with the help of this state space model. Okay, in the MATLAB directly you can develop the buck converter. Okay, this is the main requirement of the determination of the mathematical model. Okay, so next one is the So this is the state space formation for the KY converter. Here also, uh, for the on state, okay, we are writing these equations, and for the off state, we are writing these equations. And again, with the help of the state space averaging technique, d times of A1 and the 1 minus d times of the A2. And for the B matrix, d times of the B1 plus 1 minus d times of that B2. Okay, we are getting the state model corresponding to the on state and corresponding to the off state like this. And then again, we are averaging the it is the duty cycle. For that one, okay, we are getting the state model like this. And then after getting the state model, we are determining the we are building the same KY converter in the software, MATLAB software, with the help of the state space block. Okay, this is the one method, okay, to build the our physical system in the software with the help of the mathematical model. That's why I already told what is meant by the mathematical modeling. The mathematical modeling means a representation of the physical phenomena by its mathematical equivalent. Okay, the other method, with the help of the transfer function also we can build. Once you know the A matrix and B matrix, C matrix and D matrix, so with the help of this transfer function also, we can derive the transfer function. The same transfer function we can build the MATLAB. Okay, so that is about the formation of the state model for the KY converter. So, and this is the formation of the state model for the chosen active clamp forward converter. Okay, so here, so we are taking the active clamp forward converter for the on state of the main MOSFET. Okay, for the purpose of the simplicity, I am neglecting the resonant condition modes. Okay, just I am using the power transfer interval and power reversing interval. Only second, first mode and third mode I am considered to form the state model. That's why this is corresponding the state equations corresponding the first one. So here here already know the basic principle. Okay, and here there are four elements are there. One is the clamp capacitor, and the output filter capacitor. The second one is the load inductor and the magnetizing inductance of the primary winding. That means there are four energy storage elements are there. That's why here I are getting the four equations, and the order of the state space model for the isolated DC to DC converter is the 4 by 4. So here take considering the inductor current as a state variable and the capacitor voltage as a state variable, and we are trying to write the expression for the inductor voltage and capacitor current. That's why here current through the magnetizing inductance I am choosing as a one state variable. Current through the filter inductor IL naught I am choosing as a other state variable. Voltage across the output capacitor VC I am choosing as V0 I am choosing as the one of the state variable, and voltage across the clamp capacitor VC I am choosing as the other state variable. Okay, so like that I am choosing the four state variables. Those are the inductor currents and the capacitor voltage as state variable. Now I am trying to write the expression for the inductor voltage. Okay, voltage across inductor VM. So voltage across the magnetizing inductance LM is the VM. So during this mode, okay, VM equal to VG. That's why VM equal to VG. And here MOSFET Q2 is turned off. It is simply access open circuited. That's why there is no current through the clamp capacitor. That's why IC equal to 0. And here voltage across the inductor VL0 equal to voltage across the secondary winding minus voltage across the load circuit. That's why Vs minus V0, where Vs is the Vg by N. That's why Vg by N minus V output voltage across the load Vc V0 or Vc0. Okay, and the current through the capacitor C0 equal to inductor current IL0 minus I0. So therefore that is the IL0 minus I0. That's why therefore dV0 C times of dV0 by equal to IL0 I0, that is the V0 by R0. Okay, so these are the state equations corresponding to that of the on state of the main MOSFET, on state of the main MOSFET. And if you represent the same thing in matrix form, we will get, okay, these are the chosen state variables: magnetizing inductance current, voltage across the clamp capacitor, current through the filter inductor, voltage across the filter capacitor. Okay, these are the first derivatives of the state variables. So these things, okay, we are getting by writing the expression for the voltage across the inductor and current through the capacitor. Okay. So these are the state model A1 and B1 for the on state of the main MOSFET. Okay. The other one is the off state. Off state means main MOSFET Q1 is turned off and Q1 is turned on. In this case, I already told that one voltage across the clamp capacitor VC becomes more than VG. That's why it simply acts as a source for the primary circuit. That's why Vm equal to Vg minus voltage across the capacitor, and some current is circulating through the clamp capacitor, that is IC equal to ILM, and voltage across the inductor VL not equal to, there is no source voltage, that is the secondary voltage of the transformer. That's why minus V naught only we are getting here, and IC not equal to IL naught minus I naught. Okay, so similar, just with the help of these four equations, okay, we are writing the state equations here. The same state equations, okay, we are representing in the matrix form for corresponding to the off state of the main MOSFET. Okay, from this one we are getting the A2 and the B2. So by taking the average over a switching period, okay, d times of the A1, 1 minus d times of the A of, or 1 d times of A1, 1 minus d times of the A2, d times of the V1 plus 1 minus d times of that B2, we are getting the A matrix and B matrix is like this. And then if you want to build the same by taking the small signal variation in the all quantities, state variable, input variable, duty cycle, okay, we are getting the final state model corresponding to the active clamp forward converter is this one. Okay, so with the help of this one, okay, just by using the transfer function relation, transfer function dc equal to 1 minus s into C into S minus S I minus A inverse into B plus D. Then from that relation, okay, we can derive the transfer functions between the one input to the other one. So here, these are the GVG, GIG, GAMG. Okay, these are the, so these are the other transfer functions. Okay, the total 6 transfer functions is between the two inputs. One is the variation in input voltage and variation in the duty cycle. And I am choosing the three variables as outputs. One is the V naught, other one is the I naught, another one is the magnetizing current. So between the two inputs and three outputs, okay, I am getting the 6 different types of the transfer functions. Okay, these transfer functions simply nothing is there here, only the C into Si minus A inverse into B. Okay, so with the help of this relation, okay, we are deriving the transfer functions from the state model of the active clamp forward converter. Okay, this is the state model of the active clamp forward converter. Okay, so from this one, okay, we can build the same circuit in the MATLAB with the help of the transfer functions. Okay, that means these are the different techniques, okay, we are using to form the state model. Okay, so in the second step of deriving the mathematical model, okay, we are deriving the mathematical model. In the second step, we are deriving the mathematical model for the different types of the converter with the help of the state space modeling. Okay, the third one is the power stage design. Third one is the power stage design. So in the power stage design, what we need to do, first of all, after observing the working principle and after determining the mathematical model, so third step, we need to derive the mathematical some of the parameters for the power converters by using the some input and output parameters. Okay, in one case, for the buck converter case, I am taking the input voltage is the 28 volts and output voltage is the 15 volts, and switching frequency of the MOSFET is the 100 kilohertz, and output power requiring the 75 watts. So by considering the some input parameters and output parameter and switching frequency, I am deriving the expression for the L naught and the C naught. Okay, these are the filter components for this one. Okay, the calculated values, okay, here I am written 50 microhenry and the 500 microfarad, like that. Third stage, okay, we need to select the sum of the input parameters and output parameters based upon the our available source and the desired output quantities, okay, to charge that electrical vehicles. Okay, we need to select that one. So for the simple analysis purpose, okay, here I am taking these values for the buck converter case, and then here I am taking the boost converter example. I am taking the 12 volts input and 24 volts output and the switching frequency 40 kilohertz, and output power I'm expecting 57.6 watts. Okay, for special application I am designing this boost converter, that's why I'm taking this one. So and with the help of these formulas, so I have derived the filter component values L0 and C0. The same is tabulated here, 19.5 microhenry and the 25 microfarad. Okay, so like that, by considering the input parameter and output parameter, we can derive the some filter component. Okay, these are the calculated values for the KY converter. Okay, here also I am taking the input value range 12 to 18 volts, output I am requiring 24, and switching frequency is the 100 kHz and output power is the 100 watts. And with the help of these formulas L0 and C0, I am calculated the filter components. Okay, so in the third step, okay, we are trying to derive the mathematical model for that means system parameters. Okay, similarly for the active clamp forward converter also, so I am considering the input voltage VG 36 to 75 to maximum value, and topically we are taking the 48 volts, and output I am requiring the 5 volts with 20 ampere. That's why output power is the 100 watts. Okay, and the switching frequency is the 100 kilohertz. So based upon this one, okay, by taking these assumptions, okay, I am deriving the inductor value and capacitor value here. So inductor value I am getting the around 8 microhenry and capacitor I am getting the 590 microhenry. Okay, so like that, in the third step, okay, what we need to do, we need to select the sum of the parameters, input parameters and output parameters for the chosen converter. That based upon our applications, we know the what is the available source with us, at what range it is available, and what is the load requires. Okay, what the load demands, at what amount of that voltage and how much amount of the current it is demanding from the converter. Based upon that one, we need to select the input parameter and output parameter, and with the help of the available solid state switches, okay, we need to select the switching frequency. After knowing the input voltage and output power and switching frequency, simply we can able to calculate the filter components in that one. Okay, so after determining the filter components, just what we need to do, we need to observe the open loop behavior. That means behavior of the system without any controller, behavior of the system without any controller. So this is the simple buck converter. Here we are having the sum of the components MATLAB available with us. That's why is directly we can able to connect. But if these components are does not available in the MATLAB, you must be derive the mathematical model with the help of the state space averaging or small signal or anything. So from that one we can able to develop the MATLAB. Okay, this is the simple buck converter we are chosen, and these are the input parameters and output parameters, and these are the calculated values. And from that one, this is the closed loop path we are forming, and this is the developer circuit, and without any controller here we are deriving the open loop response without any controller. So from this one it is showing that one very low phase margin, only 2.44 degree we are getting here, and the frequency also 5 kilohertz only, phase frequency also 5 kilohertz only, and phase margin is very low, but the system is closely stable. That means from this one we can able to identify the uh, it is are having the some drawback. Okay, and output voltage response, time response, if you run here, we are expected 15 volts, but here only 11 volts we are getting here. In the output voltage we are getting the 11 volts only. That means there is a lot of steady state error for the buck converter without having the any input. Okay, without changing at your end. So this is the frequency response, phase margin, and the very low phase margin, and the frequency also only 5 kilohertz. And this is the time response. Okay, this time response showing the very large amount of the steady state error, only around 11 volts we are getting. And these are the disturbances we are giving for the source side and load side to observe the behavior of the controller. Okay, so this is the response. Okay, this is the second circuit, boost converter circuit. Here also we are getting the lot of disturbance in the output voltage. And third one is the, this is the KY converter Simulink model. Here also after observing disturbance, okay, here we are expecting the some 5 volts, but here it is a lot of disturbance in the input voltage. That means a large amount of the steady state error is there. And similarly, for the active clamp forward control also we can observe the open loop response. Okay, here we are expecting the 5 volts, but there is some steady state error, and very large amount of the distortions are there in the, and also the phase margin is only the 9 degrees only, and with the less at less frequency. These are the input parameters. Okay, so that means from this analysis, okay, we can by observing the open loop behavior of the system. Okay, so we can observe that one. Okay, there is a requirement of the controller, because of what is our requirement is the, whenever you are using the DC to DC converter, you need to get the regulated DC output voltage. That's why, so to get the regulated DC output voltage, we need to design some controller for that. Okay, so we will take the short 2 minutes break now. So next we will move for the design of the various types of the controller. Just to go through that of the how to design a controller, I will show the some simulations regarding the all 4 different types of the converters. Okay, we will take the 2 minutes break now.
Yeah, we'll take a quick 5 minutes break and we will start the session very quickly. Please don't sign off. Thank you.
Okay, participants, so thank you very much. And we will continue with the design of the controller for the power converters. So here there are different types of the converters are available. Okay, those are the uh, voltage mode controllers, current mode controllers, fuzzy logic, and sliding mode controllers, some other different types of the controllers. Okay, so in today's presentation, we will discuss about the design of the classical controller, simple by using the simple voltage mode controller, and then the fuzzy logic controller. I will show the simulation circuits for the all types of the converters for the voltage mode as well as the fuzzy logic. Okay, in the presentation I will explain about the for one converter I will explain the how to design the voltage mode controller, and then for other converter I will explain about the fuzzy logic, how to design a fuzzy logic controller. But in simulation I will show the uh, voltage mode controller and current mode controller for the both isolated and the non-isolated converters. Okay, so here to design a controller, uh, okay, what is the necessity of the controller? We already know that one. Okay, what is the necessity of the controller means, Rajendra sir, my screen is visible.
Yes, sir. Sir, which visible, sir. It's too much of zoom ఎక్కువ చేశారు అంతే.
Okay, okay,
Okay.
okay, we know the necessity of the controller. Okay, so from this one, okay sir, please zoom it. Okay, so from the this analysis, okay, from the response of this one, okay, we can observe that there is a requirement of the controller because of here we are getting the large steady state error, and here we are artificially we are creating the disturbance at the source side and that load side. So what is the requirement of the DC converter? DC to DC converter is the whenever the whatever may be the condition that may be change in the input parameter. That means due to the renewable energy system or due to the grid connected system, always the load on the grid connected system are varying, and it depends upon the atmospheric conditions. Always the output of the renewable energy system is changing. That's why whatever may be the condition, there is a chance to get the variation in the input value, and there is a chance to get the variation in the load also. That's why artificially we are creating the some disturbances here, and we are observing the how the system will be behaving without any controller. Okay, after placing the controller, whatever may be the disturbance you are giving, you need to get the same desired output. Okay, so then your controller will work. That's why, so by observing the open loop behavior of the system, okay, we are observing the we are identifying the necessity of the controller for a physical system. Okay, so for that case, okay, for the different cases, okay, we are observing the behavior of the open loop system, and we are observing the we are identifying the what are the different types of the controllers are available, and now we are moving towards the design of the controller for a physical system, design of the controller for a physical system. So here, simple voltage mode controller is there. Simple voltage mode controller, nothing but the most of the people knowing about that one. They heard about the KP and KI controller is there. Okay, that's why KP KI controller nothing but the most of the people thinking about the most of the people are thinking about the KP and KI controller nothing but the so KB and K control nothing but they simply choose taking the one gain block, and they are taking the one integral back here, and they are taking the some integral gain. So by adding the this proportional gain, by taking the proportional gain KP and by taking the integral gain KI, so just by changing the both KP value and K arbitrarily they are trying to changing the KP value and the KI value. So by the trial and error approach, just by changing the KI value something and KP value something, okay, they are trying to observe the output behavior whether they are getting the desired output or not. Okay, what is the desired output? Okay, so if the desired output is like this, if the desired output is like this, so your response may be like this. Okay, your response may be so like this. Okay, so with the help of this controller, what you are trying to change, okay, you are trying to reduce the steady state error between the these two values. Okay, we are trying to change the steady state error value between this one, and they are trying to change the rise time and peak overshoot of the system. Okay, so on final is settling time. Okay, that means we know the different time domain specifications: rise time, peak overshoot, steady state error, and settling time. So with the help of the controller, what you are trying to change, okay, by changing the KP and KI value here, just you are trying to change the whether the steady state error is reduced or not, whether the peak overshoot is reduced or not, and whether the settling time is reduced or not. Okay, once the settling time reduced, automatically peak time and delay time also reducing. Okay, so like that, just by changing the KPI value and KI value arbitrarily, so we are trying to design a controller. Okay, but it is not an actual approach, but it is only the trial and error method only. Okay, it is a trial and error method only. Even though you are getting the time response as you decide, time response as it is said, but the closed loop system may be the unstable by design after designing the controller by the trial and error approach like this. Okay, that means simply PI control nothing but that they are taking the KP and they are taking the integral and they are taking the KI. So directly simply with the help of the summer they are connecting the PI controller. Okay, this they told that one this is the simply PI controller. Okay, actually it is not a correct method. So the correct method is the what you need to do. Okay, so some other approach is there. Okay, that means here they are concentrating only on the time response only. The other response is the frequency response method. So in the frequency response method, what they are done? Okay, they are observing the open loop response without any controller. They are observing the response like this. Okay, here this response were already observed. That is the phase margin. These are having the phase margin is only 5.44 and the frequency at the 5 kilohertz. Okay, so by observing this open loop response, okay, they are by observing the open loop response. Okay, they are they are getting the they are assuming they require the required crossover frequency 5 kilohertz and they are expecting the phase margin required is the 52 degree. Okay, these are the their expected value. Actually the phase margin they are having the 2 degrees only, but here they are expecting the 52 degree. So by choosing the 52 degree here, okay, they are deriving the compensated pole and compensated zero with the help of the desired values of 5 kilohertz and the 52 degree. So after designing the FP value and FG value and the gain of the compensator, after designing the gain of the compensator, they are applying the same lead compensator there. Okay, they are observing the response is they are getting the phase margin 53.5 around at the 4.99 kilohertz. Okay, 4.99 kilohertz. Okay, but it's are having the some better benefit, but they are expecting the 52 degree. That's why uh, they are changing the sum of the parameter. They after that they are adding the some lead lag compensator. Okay, after adding the lead lag compensator they are getting the 47.80 degree at a 5 kilohertz, and again by fine tuning the compensator gain, they are after designing the lead lag compensator with this phase margin at 5.01 kilohertz, they are observing the output response is like this. Okay, here there is no change in the output voltage even though you are giving the disturbance at the source side and load side. Okay, that means this is the desired output. Whatever may be the condition, you are expecting the 15 volts from the converter, you are getting the 15 volts here. Okay, but previously without controller we are not getting like this. Okay, after designing the controller this one we are getting, but again we need to fine tune that one by changing the sum of the gain with reduced gain. So we are getting the with reduced gain we are getting the desired output response like this. Okay, so here from this response showing that one, here we are applying the input disturbance and here we are applying the load disturbance by designing the proper controller. Okay, here whatever may be the condition we are getting the desired 15 voltage as a output here. Okay, so this is the one of the method to design a controller for the DC to DC converter. Okay, one technique, okay, I already told to you. Okay, that is the trial and error approach. Okay, here in the controller, just by taking the KP and KI and integrator, simply you can design the PI controller or the by taking the derivative also you can derive the PID controller, but it is a trial and error approach. But this one is the accurate. It is giving the somewhat accurate, more accurate than that of the trial and error approach. Okay, this is the frequency response method. In this case, just we are drawing the border plot. So from the border plot, we are observing the what is the phase margin and what is the phase crossover frequency, and then we are assuming the phase crossover frequency and required phase margin. From that one, we are deriving the values of the compensated pole value and compensated zero value and compensated gain. So then we are observing the again open loop response. Okay, that is the frequency response and time response both, and again we are adjusting the some of the parameters, and finally we need to get the desired output response from that converter. Okay, so that the obtained result showing that one we are achieving the desired output response from this. Okay, so like that we are getting the desired output response by designing the proper controller. Okay, this is the other method of the approach. Okay, so the third other one is, okay, you know that one. Okay, it is not a simple thing, okay, to design simply by the compensated pole and compensated zero, but somewhat expertise is needed. Whoever is working on the control system area, they only able to derive the compensator by using this type of the system. Okay, otherwise most of the people they are using the simply KP and KI and some the integrator block. Okay, by the help of the trial and error approach only they will derive the they will design the some controller for the for their physical system. Okay, but it is the actual approach, okay, to design a compensator for the any type of the system. So it is the similar simple for the simple voltage mode controller. Okay, so but the we are moving for the other type of the compensator, that is the fuzzy logic controller. Okay, that is the soft computing method. So it is the main benefit of this fuzzy logic controller is the it is the low sensitive to input voltage variations, fault regulation during the load transient, robustness against the aging process of the converter passive elements. Compared to the PI controller, fuzzy logic controller provides the high performance in terms of the output voltage regulation under different operating condition. Quick damping transient. Okay, so fuzzy logic controller means what? Okay, here this is our basic compensator control DC to DC converter. And to design a converter, okay, here we are taking the output voltage as a feedback, and we are comparing with the desired output voltage by taking the V reference value, and here we are getting the error signal here, and this is the fuzzy logic controller. Okay, inside this fuzzy logic controller we need to observe write the input membership functions and output membership functions, and inside this one there is some fuzzifier decision maker mechanism and defuzzifier. Okay, in yesterday session also sir is discussed about the some basic things about the fuzzy logic controller, but in the power converters point of view I will clearly explain by taking the around 10 minutes. Okay, how to write the membership function, how to write the fuzzy table. Okay, for one converter, if you know the how to form a membership functions and the fuzzy table, then you can able to design the any type of, it is not for the power converter, you may design the same for the power system also. Okay, those who are working on the power system area, they are also able to derive the fuzzy logic controller for the any type of the system. It is the most is important in the for the this fuzzy logic control is able to implement in the hardware also with the help of the some IoT, all those things. Simple if and else rules, so it is there. So with the help of the simple if and else rules, okay, you can develop the hardware for your the power converter or the power system, whatever maybe the wherever you're using fuzzy controller, you can able to implement simply by writing the if and else relations. Okay, now the important thing is the how to form a membership functions and how to set the these values. Okay, that is the that thing is important. I will take the some more time on the designing of the membership rules here, then I will show the practical implementation of the fuzzy logic controller and the PA controller in the MATLAB as well. Okay, so here what we are taken, okay, inside that fuzzy logic controller there is input membership function, this is the fuzzifier, and the output membership function, this is the DC fuzzifier, and inside there is a decision maker mechanism. So here one thing we need to observe that one, what is the necessity of the controller? What is the necessity of the controller? We need to observe here. So the necessity of the controller is the necessity of the controller is the anybody please help me, Rajendra sir, if you are having, please help me. My screen is visible now. Hello.
Yes, sir. Visible fuzzy logic block is there, na?
I am opening the open board. Now my pen writing is visible.
No. Only slide is visible.
I am trying to write with the pen. That is not visible.
Yes, not visible.
Okay, sir. Okay, paint is visible now.
Yes.
Okay. Okay, thank you. Okay, sir. Please mute yourself. Okay, the main requirement of the controller is that one. Okay, here we are expecting the response. We are expecting the response. Okay, this if you write draw the time response here. So this is the DC line you are expecting here, but from the converter on the open loop response, okay, you are getting the response like this. So you are expecting the steady DC, but initially then the time response it is gets oscillating. It is the dynamic behavior of the system, and then it is reaching the steady state value. That means with the help of the controller, what you need to do, we need to uh, avoid these oscillations, and steadily we need to get the desired output response. That means the deviation between this desired output and the present output we are called as the error. Okay, here we called as the error. So after some time, by using the controller, after some instant, okay, your response may be changing like this. Okay, your response may be. So now this is the state. This much is the steady state error. But the after some instant of the time, your response may be, that means somewhat reduction in the steady state error you may achieve. So after some instant, okay, this is the waveform. Now if you are observe the error, so previously it is the error, now the error is this much. That means the second case we called it as a change in error, CE. So the first one is the error after working of the controller. After some instant the time, again if you sense the output, and if you are if you are calculating the error signal, that is called as a changing error. Okay, that means while forming the fuzzy logic controller, we need to take the two parameters. One is the error, other one is the changing error. Okay, error signal and the changing error signal. So So that's why, okay, here in the fuzzy logic controller, here we are taking the two. One is the error signal here. Okay, error signal, nothing but by comparing the present output with the desired output value. Okay, here we are getting the error signal. Okay, this is the error signal, and the changing error. Okay, here we are taking by using the some derivative term. Okay, the derivative of the error signal is the changing error signal. That means the inputs for the this fuzzy logic controller is the one is the error signal, other one is the changing error signal. That means there are two inputs are there. One is the error signal, other one is the changing error signal. And the output voltage is what? Only one. Okay, that is the output on duty cycle we are expecting from the output of the fuzzy controller. Okay, that is the output signal. That means for this converter there are two inputs are there. One is the error signal, other one is the changing error signal, and third one is the output too. Okay, error signal, changing error signal, third one is the output to membership. Okay, that means for these three we need to write the memberships. Okay, error, for the error signal we need to form the membership, for the changing error also we need to form the membership, for the output also we need to form the membership. Okay, so for this error signal, okay, here we can take the multiple of the that means odd quantity. One is the either 3, 5, 7, 9, like that we are taking. So in this case they are taking the 5. They termed the first one is the zero error, negative small, negative big, positive small, positive big. So like that, okay, here they are taking the different ranges: negative big, negative small, positive big, positive small. Okay, for the both change input error variable, other one is the changing error variable, and the output also they are taking the zero error and the output variable. Okay, so methodology we are following, a methodology we are following to design a fuzzy logic controller is the first of all we need to know the basic, okay, the same thing, principle of operation, then mathematical model. Third one is the we need to observe the open loop response. Okay, from that open loop response, okay, we need to observe the what is the range of the input signal we are getting, what is the range of the error signal, okay, we are getting. Okay, that means by observing the open loop response like this, one is the desired output and the other one is the present output. By observing the response like this, so we need to identify the what is the range of the error signal and what is the range of the change in error signal and what you are requiring. Okay, what you are requiring. Okay, that three, okay, you need to calculate. Okay, how you know the range of the error signal? Nothing but the, if you draw the some dotted line between the this maximum value of your response and the minimum value of response. Okay, so the magnitude between these two is giving the range of the error signal. The range of the changing error also is a similar thing, only because of the changing error we are getting after some instant of the application of the controller. That's why the magnitude of the changing error also in that range only. Okay, error and changing error, so almost are having the some nearer value. That's why how to derive the range of the this error signal. So by taking the range only we are able to uh, observe put the span of the membership functions. That's why, so by taking the time response and by drawing the lines like this, okay, by observing the uh, deviation between the maximum value to the minimum value, okay, we can we taken it as a range of the error signal. The same range we are taken for the changing error. Okay, so but here they termed it as a negative small. Okay, they termed as a negative big, and then they are taking the negative small, and they are taking the zero error, and they are taking the positive big, and they are taking the positive small they are taken, and then they are taking the positive big also. Okay, so what is the how to define the these ranges? What is the value of the negative big, what is the value of the negative small, and what is the value of the zero error, what is the positive small and positive error? So for that I simply taken one example. So here the zero error, nothing but the, we must all of you we know about the bike riding. So that's why I am taking the simple example for that. Okay, for example, my target is I need to drive the bike by the 50 kilometer per hour. Okay, my expectation is that I need to drive my bike with the 50 kilometer per hour, but at the present I am getting the some 60 kilometer per hour. That means my change speed variation is in between the 50 kilometer to the 40 kilometer per hour. That means what is the span I am getting, what is the minimum range or deviation between the minimum range and maximum range? Error value is the 20 kilometer per hour. Okay, now the error range is the 20 kilometer per hour. So but in between what I need to get at 50 kilometer, I am getting the zero error because of my expectation value is the 50 kilometer only, but it is ranging from the 60 to 50. So that means if the 50 is the our required value, at 50 I am getting the zero error. That means at 50 kilometer I am taking the at 50 kilometer error. For example, I am taking the at 50 kilometer I am taking the zero error. I am taking the zero error. So what is the positive small? So for example, if you are comparing the present output with the desired value. Present output means if you are having the 60 kilometer per hour, but the present that means you are requiring the 60 50, but the present output is the 60. So what is the difference between the present output minus desired value is the 10 kilometer. So therefore 10 kilometer is the positive error I am getting. Okay. So that 10 I am taking as the positive biggie here. Okay. That means at a 60 kilohertz, at a 60 kilohertz, I am getting the maximum deviation is the 10 kilometer per hour from my desired value. That's why I am taking the positive big is the 10. So at 40 kilohertz, what I am getting? I am getting the negative value. So as because of here I am getting only 40 only, but I required is the 50. That's why I am getting the minus 10 deviation. That's why minus 10 I am getting. Okay, so for the negative small here I am defining the minus 5. For the positive small I am defining the plus 5. What I am taken here, I am taking the desired value is the 50 kilometer per hour, but I am observing the what is the minimum deviation, maximum deviation in the my output. The deviation is in between the 40 to 60 kilometer. So in between 40 to 60, I am getting the 50 is the our desired value. That's why 50 kilometer I am setting it as a zero error. Okay. So minus 5, okay, negative side minus 5, minus 10 I am taking as a for the negative small and negative big, positive small and positive big I am taking here the for plus 10. So like that by observing the maximum deviation and minimum deviation between the positive error and negative error, I am defining the values for the negative big, negative small, zero error, positive small, positive big. Okay. So similar manner I am taking the same table for the changing error also. But the what is the output I am expecting? Okay, for the output also we need to write the membership functions for the negative small, for the negative big, as well as after that one negative small, then for the zero error, then for the positive positive small, then for the positive big. So these are the different outputs. Okay, I am taking. Okay, for the output also we need to define the value. Okay, for example, if we are getting the 50 kilometer per hour, for example, if you want to get the deviation from the 50 kilometer, what is the input for your bike riding? Your input is the acceleration. So by changing the acceleration from minimum value to maximum value, we are able to get the variation in the speed. Okay, but in the power converter side, what is the how to get the variation in the output voltage in the output to side? Okay, in the power converter side, the output voltage variation depends upon the duty cycle. The duty cycle is varying in between the 0 to 1. Okay, the duty cycle is varying between 0 to 1. So for example, in that example, we are taking the 28 as input. Okay, and at present if you are getting the some 24, the deviation is the some 4 volts. Okay, that means your variation is in between the some plus 4 to that of the minus 4, and this required output voltage if you are getting at the 50% of the duty cycle, if you are getting the desired output at the 50% of the duty cycle, so therefore the zero error value is the 0.5, because of at 50% you need to get the desired value. So corresponding to the deviation of the plus 4, okay, if the negative big is the some 0.4 or the some positive big is the some 0.6, and here 0.45, or the here some positive small is the 0.55. Like that by using the duty cycle formula, you need to set the your output variable values. Okay, So corresponding to the zero error, you need to set your desired PWM signal, and then based upon the variation between the minimum value to maximum value, you need to set the values of this one. Okay. So like that we can set the values of the membership functions for the input variables as well as the output variables. Okay, the input variable values, okay, output variable values, and then so we need to form the one table. I think this table is visible. Okay, this is the important table. Okay, we need to form the this table. Once if you know the table, then we are able to design the controller for the any type of fuzzy logic controller for the any type of the system. So that's why, so how to form the table, nothing but the, so error and changing error, these are the variables are the error signal, negative big, negative small, zero error, positive small and positive big, and these are the variables of the negative big, negative small, zero error and positive small. For example, in the bike riding, so we can observe that we are expecting the error signal is zero error, nothing but the, if you are expecting the 50 kilometer per hour, at present you are also running at the 50 kilometer per hour. What about the, yeah, what about the error at that instant? Error there is no zero, because of you are expecting 50 but you are running with the 50 only, that's why zero error at that instant. Same, what about the changing error? That is also zero. So for the zero error case, and both error and changing error both are zero error, okay, you need to write the desired output also is zero error. Okay, so for example, if you are running with the 60 kilometer per hour, that means if you are running with the 40 kilometer per hour, so that is the negative big value. So and changing error also a large value, negative big. So if you are both are negative big, what you need to do? If you are running with the, for example, at 50% at zero error means 50%. So but you are having the 40 kilometer per hour, nothing but let us assume that 40% duty cycle is there here. So if you want to get, if you want to increase the output voltage, what you need to do? You need to increase the duty cycle value. So to increase the duty cycle value, what you need to do? You need to move the duty cycle from 0.5 to the zero point 0.6. So for 0.6 we are defining the positive big value. That's why if the error and changing error both are negative big, you need to drag towards the negative big. Okay, so if the both are zero error, you need to set for the zero error. If the both are negative big, you need to set for the positive big. The other case also we can observe, if the error signal is the positive big and the changing error also positive big, let us assume that you are expecting the 50 kilometer per hour, but you are running with the 60 kilometer per hour. That means your error is the plus 10 and changing error also plus 10. So both are the positive big. What instant, at that instant what you need to do? You need to drag the your duty cycle at the, you need to in the case of the bike riding, you need to reduce the acceleration. Reduce the acceleration nothing but the negative big. That's why. So you need to put the negative big here. Like that we need to observe the different conditions. Okay, once again I will explain. See, if the both errors are zero error, we are getting the zero error. If the both are the negative big, you need to drag with the positive big. If both are the positive big, you need to drag with the negative big. In some other cases, one is the zero error, other one is the negative small, you need to drag with the positive small. If the one is the positive big, other one is the zero error, you need to drag with the negative small. Like that, you need to form the table by simple. This is the simple example. Fuzzy logic controller we can get easily by just observing the our real-time principle. So like that, we can form the fuzzy logic table. By using the fuzzy logic table here, we can get the output responses like this. So if time permits, I am trying to explain about the some real-time example by using the fuel cell system, DC to DC converter, electrical vehicle, charging, battery charging. I am trying to. So regarding this thing, I already developed that one. Okay, this is the our MATLAB simulation, fuel cell subsystem, DC to DC converter. This is the battery we are trying to charge. With the help of the fuzzy logic controller, we can trying to develop the fuzzy logic controller for this. Okay, so this response showing the whatever this is the input voltage response, and these are the responses we are getting whatever may be the condition. We are trying to get the constant voltage and constant charging current, and the battery is trying to charge. Okay, this is the state of the charge of that one. So the final observe is the conclusion is the you can able to get the uh, as compared to the PA controller, fuzzy logic controller, you are having the simpler dynamics. No mathematical model is required for the fuzzy logic controller. Just by writing the if and else rules, okay, we can able to form the fuzzy logic controller. There is no problem with the transformer saturation, better noise reduction, closed loops stability also there. Okay, so just we will move switch to the some MATLAB. Okay, I will share the my MATLAB screen. Uh, by using the by showing the from that MATLAB, okay, we can find something about the. Just a minute, I will open the MATLAB. I will show the some of the real-time implementations, okay, for the buck converter, active clamp forward converter, for both voltage mode control as well as the fuzzy logic controller. Okay, then we will get the some basic idea about how to design a controller for the power converters. I think my screen is visible now. I'm trying to open the buck converter. Okay, here we are taking the V in is the 28 volts, so V15 duty cycle I'm calculating the L and C. Okay, these are the calculated values. Okay, we are taken. So and then by opening the voltage mode the simple voltage mode controller block, we will run the simulation. Just wait, simulation is starting.
Push it.
Okay, this is the state space model we are derived. Okay, the same state space model ABCD matrices I am written inside this one. I think my screen is visible for all. ABCD matrices, whatever the things we are determining from the state space model, say the same we are written here. Uh, ABCD matrices. And this is the designed controller. First we are derived the PI controller, and then we are adding the PD controller, combining these two PID controller we are getting. So by changing the gain value by somewhat, okay, we are forming the some complete closed loop controller. And then this is the voltage disturbance and this is the current disturbance. So for the input voltage of the 28 volts, we are expecting the 5 volts by giving the 28 volts input. So these are the results we are getting. 15 volts output we need to get. Here we are applying the disturbance. So this is the voltage disturbance. 5 volts I am giving disturbance at the 6 0.6 millitime. And this is the current disturbance I am getting at the 0.3 millitime minus 5 ampere. So for the minus 5.3 minus 5 ampere case, the current is added by the 5 for the 5 ampere output current. That's why it is become to 10. But the our main concentration on the voltage, even though you are getting the load disturbance and the voltage source disturbance, okay, at 0.06 we are giving the voltage disturbance.
సార్ ఏమి కనపట్లేదు సార్ మీరు
అవునా?
ఏం చూపిస్తున్నారు?
మ్యాట్లాబ్ షేర్స్
ప్రోగ్రామింగా లేకపోతే అవుట్పుట్?
అవుట్పుట్ వోల్టేజ్.
ప్రోగ్రామే కనబడుతుంది, అవుట్పుట్ కనబడుతుంది. ఓకే.
So this is the converter. Inside this one we are placing the ABCD matrices, and inside this one we will show again because it is not visible. So inside this one there is some PID controller. From the frequency response, okay, we are having the PID controller. Okay, that thing we are placed here. So then I will share the again a Simulink model. Oh, just a minute. Okay, okay, I will share. I am sharing. Okay, so inside this one I am placing the ABCD matrices value, and here I shown the controller parameter, the transfer function I am written. So here I am giving the voltage disturbance, and here at 0.06, at point 0.03 I am giving the current disturbance. So for that we will get the even though you are giving the voltage disturbance and the current disturbance at both the cases, okay, you need to get the desired output response from that. So after running this one, we will get the desired response. Okay, I will share the outputs now. So even though by giving the 0.03, at 0.03 we are giving the current disturbance, and at 0.06 we are giving the voltage disturbance. So both the cases, okay, we are getting the desired output voltage of the 15 volts here. Okay, so this is the Simulink model for the buck converter case. Okay, again I will share the some other one for the active clamp forward converter. Okay, that is non-isolated, isolated DC to DC converter, and it's the fuzzy. So okay, so here I am giving the voltage input 48 volt, voltage 5 volts, L naught and C naught, magnetizing inductance, clamp capacitor, I naught, R naught, all the input parameters we are showing. Okay, the same thing we are written here. So this is the file name, model file name I am written here. Automatically by running this one, it automatically opened, and then to include the fuzzy logic controller. Okay, one aspect how to use the fuzzy logic controller here is the fuzzy. You need to type it the fuzzy here. You need to type the fuzzy here. So if you write by typing the fuzzy in command window, okay, we will get the, you will get the fuzzy block like this. Okay, and here at file we need to import the file from the developed model, trial 3. So then it will automatically import the .fis from the saved system. By using that one, So this is again, after developing this one, we need to export it to by writing the file through export to workspace. So we need to export it to the workspace here. Now we need to open the active clamp model file ACFC with fuzzy. Okay, here we need to write the fuzzy here for export to the top system. So then okay, this laptop having the some running with slow. Okay, it is we will conclude the today's session, and I will share the basic PI controller and fuzzy logic controller for the simple buck converter through mail ID. So you can go through that one, and if you have any problems in implementing, okay, you can contact me. I will explain about. So with this, I am ending the session now.
Thank you,
Okay.
sir.
So thank you very much. Thank you.
Thank you, sir. Thank you very much. On behalf of our Tribute Department faculty and students, once again, thank you very much, sir, for accepting invitation to act as today's resource person, sir, and giving the valuable information. Thank you very much, sir. With this, we'll conclude the session, sir.
Thank you, sir. Thank you. Thank you very much. Sir, queries ఏమన్నా ఉంటే అడగమని సార్.
If anybody having any queries, you may ask now. I have given already the permissions. Varitananda and somebody else. If you have any queries, you can ask now. Otherwise, we will conclude the session. Okay. Thank you very much. Sir, nobody raising any.
Hello.
Okay.
Hello, sir.
Sir. Madam, చెప్పండి.
Sir, I have a doubt, sir. When you are
Madam.
selecting the switching frequency, you said
Madam.
it is based on the solid state switch.
Yes, madam.
You select switching frequency. You
Yes,
selected
madam.
it to be 100 kilohertz for
Yes,
a
madam.
boost converter also. So how
Yes,
did
yes.
you select it, sir? Switching
Based upon
frequency.
the rating components available at the market, we need to select it, madam. First of all, we
From the
need to select.
components, sir?
Yes, madam. First of all, we need to select the rating of the voltage and current. At that, if the component is able to withstand that voltage and current value, then we need to go for the high switching frequency. If your switching frequency is high,
Not
the
clear. Excuse
madam.
me, sir. Your voice is not clear, sir.
Madam, first of all, we need to calculate the voltage across the switch and current, maximum current through that switch. By observing the operation of the circuit, we need to calculate the how much amount of the current is circulating through the switch, and we need to calculate the voltage value. After calculating the both voltage and current, we need to check the data sheets available with the different manufacturers. So if the manufacturer is showing that that much amount of the voltage and current is withstandable, then we need to select the frequency of that switch, madam. The same we can use here. Based upon that switching frequency only, we need to calculate the inductor value and capacitor value.
Thank you very much, sir. Your presentation was really good.
Thank you, madam. In the MATLAB, I will show that one, but my system is slow. That's why I will share the buck converter presentation, MATLAB files to also through mail. Can go through that one. If you have any doubt, please feel to contact us. No problem. We will explain. Thank you, madam. Thank you very much.
And one more, sir. I have one more
Madam,
doubt, sir. We
madam.
usually say DC to DC converter is a voltage regulator.
Yes, madam.
Correct, sir?
But indirectly, it is controlling the current also. But most of the cases, we say in terms of the voltage only. Because of in the AC, we are using the transformer. The same function in DC, the solid power converter will doing. That's why simply we termed it as a voltage regulator, but indirectly it is controlling the current. Because of in the low voltage, high current applications, we are using the DC to DC converter. That means indirectly we are trying to increase the current value. That means indirectly we are changing the current. But generally we termed it as a voltage regulator.
But in case of low current, sir, high voltage and low current.
High voltage, low current also we are using the boost converters, the similar KY converter and boost converter. Okay, in that case also we termed it as a voltage regulator only.
Then why extra feedback is required, sir? If it is the voltage regulator.
Extra feedback meant nothing but that feedback is required to get the desired output. Man. Generally, we are using the renewable energy source or the grid connected systems.
Yes,
Even though
sir.
you are using, even though you are using the grid connected system, every second our load is changing. That's why that means you are getting the voltage fluctuations at the input side. And if you are using the renewable energy source also, from time to time there is input fluctuations. So whatever may be the input voltage variations, if you are using the DC to DC converter, the function of the DC to DC converter is that it need to regulate the DC input voltage, and you need to give the desired output, constant output voltage. That's why we need to form a controller. So in that controller, there are different types of controller. That's why in the controller point of view, you are getting the extra feedback. If you're confident about your input voltage is constant, then it is not required. But always the practical system, it is not possible to get the input voltage is constant. That's why the extra feedback is required, madam.
Okay, thank you, sir.
Thank you. Sir, thank you, sir. Okay, if there is any.
Good evening.
Madam.
Madam, your voice is very low. We are not able to listen. It's not audible.
Hello, sir. It is audible, sir?
Yes, madam. Yes, madam. Now it is audible. Please.
Sir, the switching on and switching off. Like how you are giving, sir? Any particularly?
Madam, after controller design, after output of the controller, from that controller we are getting the DC signal only. By comparing the DC signal with the some sawtooth waveform, that means in the MATLAB we are using the some sawtooth waveform, but in the real time there is some pulse generator techniques are there. By using that components, we are developing the gate signal.
Okay,
so
sir.
with the help of that gate signal, we are giving the turn on and turn off. Where that means the gate triggering circuits are there, madam. With the help of that one, we need to give the gates pulses for the turning on and turning off of the switches whenever we are required.
Okay, sir. Okay, sir. Thank you, sir.
Anybody else?
Okay, sir. We will continue the. We'll close the session.
Sir.
Sir. Tell me, sir.
Hello.
Hello. Please continue.
Hello. Somebody asked, said, sir. Maybe connection problem, sir. We will conclude the session, sir. Thank you very much, sir.
Okay.
Hello, sir.
Sir,
what is the purpose of P and PD controller, sir?
What is the
purpose of PI and PD controller?
purpose of PI and PD control? Nothing but the in the DC to DC converter applications, there is a chance to get the variation in the input voltage to the DC to DC converter, and there is a chance to get the load side variation also. And once designing of the internal components of the DC to DC converter, due to the aging effect, there is a chance to get the variation in the inductor value and capacitor value. That means the causes may be the input side variation, or the load side variation, or the parameter variation. Whatever may be the case, we need to get the desired output, constant output from the DC to DC converter. So to get the constant output, we know the from the open loop system it is not possible to get the constant output. That's why to get the constant output, we need to form a closed loop circuit. In the closed loop circuit, there are different types of the controllers are there. In that, one type of the controller is the PI or PID or the PD or fuzzy or sliding mode, like that. There are different types of the controller. So that is the necessity of the controller.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir.
Okay, sir. If anything else, you can.
Okay, sir. We will conclude this.
Thank you very much. Thank you, one and all.